In this video, we'll look at some more examples of using u-Substitution to compute different indefinite integrals. Let's look at the example with 4x up in the numerator and then 1 plus 4x squared in the denominator. I'm going to take u to be that denominator, and the reason why I do that is its derivative will be linear, and I have a linear numerator. If I differentiate that, I get 8x. I don't see 8x in my integral, I see 4x up top, so I'm going to divide everything by 2. Write it as a differential first, and then divide everything by 2. And I have 1/2 du is 4x dx, and we can make our substitution now. I'm going to have the integral, and it'll be 1 over u, because that's all that appears in my denominator. And then the 4x comes at the cost of 1/2 du. Again, this is just a natural logarithm. And if I back substitute, it's the natural log of 1 plus 4x squared. Now 1 plus 4x squared is always positive. If you take any number and square, it will be positive, and if you add, or non-negative, and if you add 1 to it, it will be positive. So the stuff inside that absolute values is automatically positive, and I really don't need absolute values there. So I'm just going to replace them with parentheses. And then a 1/2 power, or a multiple of 1/2 in front, in one of the properties of logarithms says that we can bring up the exponent. And a 1/2 power is really just a square root, so we could rewrite it as the log of the square root of 1 plus 4x squared. Let's do a similar example. I've got the exact same expression, but I didn't put the x up top. I just have 4 up top. The substitution that we did above would not work now because you wouldn't be able to substitute out the differential part that had the x attached to it. You don't have the 4x anymore, you just have 4 dx. What I'm going to do though is recognize that this is roughly our inverse trigonometric form. It's the arctangent form. It looks like 1 over 1 plus a quantity squared. I have this 4 that I just pulled out front. That's not that big of a deal, but the stuff inside the parentheses that's being squared is 2x. And so this is just the arctangent form, but it's not of just x squared itself. It's 2x inside there. So we're going to do a substitution of 2x. The differential will be 2. And if I double everything, I get 2 du is 4 dx, and I did that because I see 4 dx there. And we can carry out the substitution now. It's really 1 over 1 plus u squared. And 4 dx comes at the cost of 2 du, so we have just 2 times the arctangent of u. And we can back substitute 2x in, and we're done. Let's look at some more examples. Here's the integral of tangent of 2x. It's not immediately clear what its antiderivative is, but if we rewrite it in terms of sines and cosines, we can make some progress. I see sine over cosine, and they're roughly derivatives of each other. In fact, if I take u to be cosine of 2x, its derivative is roughly sine of x, and that's what's appearing in the numerator. I'm going to differentiate it. Remember, the derivative of sine is minus sine. The derivative of cosine is minus sine. I leave the 2x alone, and the chain rule says multiply by the derivative of 2x, which is 2. Let's write it as a differential. I'm going to divide everything by 2, and I have minus 1/2 du is sine of 2x dx. So we can carry out the substitution now. Cosine's in the denominator, that was our u, so it'll be 1 over u. And then the sine of 2x dx comes at the cost of minus 1/2 du. So I'm going to put the minus 1/2 outside, and there we have another natural log antiderivative. So minus 1/2 of the natural log of u, and then you can put in the cosine back in for u. That's a perfectly suitable answer. I just want to show you maybe some different ways of writing this, more as review. For instance, that negative in front can be thought of as a -1 exponent inside the logarithm. And a -1 power really means reciprocal. The reciprocal of cosine is a familiar function to us. It's the secant, so instead of 1 over cosine, I've written that as secant of 2x. We can do the same thing. The 1/2 is really an exponent to the 1/2, which is just a square root, so we might write this as the log of the square root of secant. And in fact, this is fairly common that we want to integrate tangent, and it turns out the integral of tangent is the log of secant. Let's look at another example. Here I've got 4 times e to the 2x times tangent of e to the 2x. It looks like quite a complicated expression until we realize that the exponential part is its own derivative. If I take u to be e to the 2x, its derivative is e to the 2x, and don't forget to use the chain rule. Derivative of 2x is 2. I don't see, well, I'm going to divide everything by 2 here and write everything in differential form, and I have 1/2 du is e 2x dx, and we're going to make this substitution. I had a 4. It's going to be tangent of e to the 2x, and that stuff in there is just u, so it's going to be tangent of u. And then the differential part, dx, comes at the cost of, so notice it's e 2x dx. That comes at the cost of 1/2 du, so 1/2 du. And if we simplify, that would be 2 integral of the tangent of u, and we just wrote down the antiderivative for that. So we could do what we did with the substitution before, or we could just apply that formula. It's 2 times the natural log of secant of u. Finally, back substitute secant of e to the 2x. That's a totally appropriate answer, but we could do some of the same things that we did with the power, for instance. The 2 in front becomes a square, and when we write trig function powers, we usually put the power in the middle, so I've written it there. And if I square that secant, it's automatically going to be non-negative, so therefore the absolute value is superfluous, and I can drop that if I prefer.